can take that.
So today we're doing the last lecture that's actually going to be relevant for the project. After this, there's one more lecture where we'll just talk about some other related topics, but they're not going to be on the project anymore. And then the final two lectures will just be presentations. So your final presentation, the check-in, is this week, the last check-in. And then the actual presentation will be due in about 1.5 weeks. So make sure you start getting to a conclusion on that. Project 6 is going out today. So for Project 6, it's going to be a little bit different than the past projects. In this case, there will be 3 challenges again, but you only have to do 2 of them. So out of the 3 challenges, choose 2 of them that you think are most interesting to you and just do those 2. You can do the third one as extra credit, kind of similar as like the previous proposal where you say you can make the proposal for extra credit and do that. You can also do the third challenge for that. But yeah, any question like the general course state so far, or currently? All right, then let's get started with today's lecture. So we'll be talking about another program analysis technique that kind of, to a degree, builds up on the previous ones, but is very different in many ways, being symbolic execution. Yeah, just kind of thing. So today's content, we're just going to talk about symbolic execution, talk about some of the things that go into it, like constraint solving, a tool called Z3, talk about different engine types, and at the end we're going to showcase how to some practical examples of using symbolic execution. So, an introduction, symbolic execution is a technique that was introduced in the mid-70s for program analysis. Back then it was very different than it is now, but that's kind of when the ideas for it started, so it's a very old technique. So the main idea of this is to transform a program into a mathematical equation and solve it for some constraints. So it sounds weird, but we'll showcase some examples of how that actually looks. And this mathematical equation can then be solved using a SAT solver. So in 311, if you took Dog Newton's class, you probably talked about about SATs, or like how you like Boolean formulas that you solve for, like if they're satisfiable or not. And that's kind of the idea that on which symbolic execution relies on. In one of the earlier lectures, we talked about symbolic data versus concrete data. Just to quickly reiterate on that, because that's going to be very relevant for today. So in terms of the program, concrete data is when you have the actual data mapped basically itself. So if you have like an integer, then the concrete data would be maybe that the integer is equal to 5, or that the integer is equal to 3, whatever it actually is during execution. With symbolic data, you kind of set up an abstract symbol for it. So you might say that the integer could be anything in range negative 255 to 255, if it's like an 8-bit integer. Or if you have a check, like if x is bigger than 3, you go into this, then you can say that if we're at this location in the program, as a symbolic variable, you could say that x always has to be bigger than 3, kind of in the same notion as like the program invariance that we talked about a bit. And if we're talking about concrete values, then x might be 4, x might be 5, it's just one of them. Symbolic, you represent anything that it could be at this point, kind of. So the general idea is that the instructions of a program would be simulated by this type of symbolic execution engine. And instead of just running the program where all of your data would be concrete, so if you run a program, you give it some inputs, it does calculations, you have your memory, everything is done based on like your memory, your registers, your concrete data pretty much. With symbolic execution, you're going to simulate it through one of these engines, and instead of dealing with concrete data, they're going to deal with symbolic data. So if you hit a branch like that, you could say if it goes in here, x would not be equal to 4, but x would be equal to any value larger than 3, for example. And we're going to talk a bit about how that is used in practice and how that's useful for security. So this symbolic execution engine kind of maintains a symbolic or a Boolean formula throughout the entire program. And this basically is used then to satisfy various conditions. Maybe I'll just go and showcase an example in a second, because I think from this alone, so it doesn't probably not going to make too much sense. And yeah, so it generates some form of formula, and this formula is then passed to like this SAT solver, which then solves this formula basically for us. And let's just look at an example. So we have a snippet of code here. It's a small function. This function takes two inputs, x and y. And then if x is not equal to 0, it takes this branch. Also, it just prints out invalid. And then if y is bigger than 0, it calls gets. It also calls exit. So as someone who does security, something that we would want to know about this program, for example, to find a bug, is can we get to this gets call? And if so, what kind of input would get to the gets call? In this case, a very small function. We could very easily do it manually. We could see, okay, x shouldn't be 0, so maybe if x is 1, we go in here, then y needs to be bigger than 2. So if x is 1 and y is 3, we get the gets call. But if this is a bigger program with much more complicated kind of constraints to get to the gets call, this is kind of when we start using symbolic execution. So let's say we have this engine that starts executing this, the symbolic engine. So instead of dealing with concrete data, it now says, okay, x can be any value from negative 2 to the power of 32 to 2 to the power of 32. Same with y. So it's no longer a concrete value, which could be like 3 or 4. It's now like this formula. Then we start executing the code. We get to the first branch here, if x is not equal to 0. Then symbolically, the engine could say, okay, at this point, we can set up a symbolic variable for x is not equal to 0. And the same at this point. Let's actually draw this out a bit. So we have the initial part where we say that x is some value in like integer range, and the same with y. So this is our initial state. When we call the function, x is an integer and y is an integer. And we get to the first branch. And at this point, there are two things that can happen. So assuming we want to still keep track of everything symbolically, we want to model both. So we can then split this state up into two states. And for one, we then say that x is now not equal to 0, because that's what we were required to get into this if statement. So now x is not equal to 0, and y is still can still be some arbitrary integer. It's not relevant yet. And we also have a different state, which is if we don't get into this if branch, but we hit this else branch, we can now say that if we are here, then x is in fact equal to 0, and y is still some integer. So these are kind of the formulas we're setting up at this point. Okay, so now we want to continue. We want to get into the next two branches here. So we'll move on to the next slide. We then make these constraints that we're setting up a bit more strict. So now at this point we hit, if we hit the second case, so this one, there's nothing else to hit, just print invalid that x is the function. So from here we're kind of at an exit. There are no more paths to get here. Okay, so let's look at this one, the more interesting state. So we now know that x is not equal to 0, and we're at this point at the next if statement. So now there are two more cases, one which is hit if y is larger than 2, and one which is hit if y is not larger than 2. So we can once again, we have our state here, and we split it up into two different states again. And for one of them, we now know that x needs to be not equal to 0. And then now in this case, we also know that to reach this, y needs to be larger than 2. So these are now our constraints to hit this gets call here. Same with for the exit. In this case, our state would be x is still not equal to 0, because that was required to get there. And then y now needs to be smaller or equal than 2. And at this point, we now have these formulas, which we can then pass to some solver. And this solver would then give us values for x and y that maintain everything in this. Kind of like when you were in 5th grade taking math class, and they give you kind of like a set of formulas with two unknown variables, and they tell you, solve this for which x and y would make these formulas correct. That's basically what these types of SAP and SMT solvers do, just in an automated fashion. So the symbolic execution engine executes a program symbolically, simulating everything, generates these types of formulas, and then passes these on to the constraint solver. We'll talk a bit more about the constraint solving and give some more details of that later, but that's the general idea of this. And at this point, we could then say, okay, so we found the gets. How do we reach the gets? Well, this is the formula that reaches the gets, and then we pass it to the constraint solver, ask it if this formula can be satisfied. If it says it can be, we can ask for a model, and then it would give us like a value for x and a value for y that would satisfy it, and basically an input that we could use to reach the gets call. And that's kind of the basic idea of symbolic execution. And we'll talk later about more how this is actually useful for us. Any questions so far? Yeah.
And the sort of like the data that Symbolic Execution gathers, like, oh, like these values will get us to this branch, and that also means like as an input for the fuzzer to help it like track better inputs.
Yes, we'll talk specifically about fuzzers later. It's one of the later slides. But yes, in theory it can be. And it has also been done in practice. Any other questions? Okay. So let's talk specifically about the constraint solving part a little bit first. We are not going to talk about the specific algorithms and stuff for this, mostly because it's not super relevant to us. From our view as vulnerability researchers, we can view this constraint solver as a black box to a degree, where we generate this formula, we give it the formula, and it gives us a result. I think classes focus more on like theory, like extensions of 311, or constraint solving is also very relevant in AI from what I've heard. I'm not really into, so I don't really know the specifics of it, but I think a lot of those types of fields would cover the specifics of how this works a lot more. We're just going to consider more of a black box that kind of works. Just talking a little bit about it though. So let's start off with SAT. This is the general satisfiability. If you've taken 311, the professor probably told you that SAT was the first problem that was proven to be NP complete. This is kind of the start of a large branch of the theory and algorithms and all of that stuff. And it's basically for just Boolean and satisfiability logic. So you give it some form of Boolean statement, like x is not equal to y, and I don't know. It's like the algorithm or the theoretical formula, it's like, and y is equal to false or whatever, and then you might solve it to figure out what x is. And kind of this, as it gets larger and larger, it gets harder and harder to solve, and the algorithms to solve this are all NP complete, and it's a very hard problem to actually solve by computers and cannot be done efficiently. So satisfiability, so SAT operates purely on these Boolean formulas, so you don't have integers, you don't have arrays, you don't have anything of that sort. You just have Booleans, and the Boolean formulas like and, or, not, that type of stuff. Yeah, kind of like another example here. What Boolean values for P and Q satisfy the following statement, P and not Q. So you might say that P would need to be true, and same with Q. So that's kind of the general idea between SAT. And then there's SMT, which is kind of an extension of SAT. And this kind of, it's basically SAT, but more complex. So it's still NP complete, or in some cases even undecidable, making it even harder to solve. But this kind of extends on SAT to not only support Booleans, but also support other data structures like integers or character arrays and so on. So as you might expect, this gets a lot more difficult because suddenly it doesn't only model Booleans, it also models things like addition or multiplication, or x is larger than y, all these things that actually occur in programs, SMTs can model and solve for as well. This is referred to as predicate logic in general. And so this would be, for example, a formula that a SAT solver could not solve because it's just Boolean, but an SMT solver could. So like x plus y times 3 is equal to 4 minus x. It's like a formula where you could find values for x and y that would solve the equation. So let's look at an actual SAT solver and how it looks. If you have a Linux VM set up, you can actually just follow along with the example. This is not what I wanted to open. That is. Okay. So I believe the command for this is pip3 install z3 solver to just install it. And let's zoom in a little bit. Okay, so pip3 install Z3 solver to install it. Then you can just launch a Python shell, and I believe that's right. Yes. Okay, and at this point, so we now have C3 imported into the Python shell. We can now declare some integers, for example. Say, so let's start by declaring two variables, x and y, both of which are integers. So Z3, first of all, let's probably talk what it actually is. It's a constraint solver that is probably the most popularly used one, at least as far as I'm aware. It is mainly being developed by Microsoft, and it is a full-on SMT solver that they've done a lot of work in optimizing it, making it work well. And in general, it seems to be pretty good. I'm not an expert on it, but yeah. Okay, so here are the basic steps for now. We declare two variables for now, and we create a solver. And this solver is what we kind of operate on. So there are then two commands that we care about. S.check, which tells us if all the constraints on the solver are actually able to be satisfied. In this case, we haven't put on any constraints yet, so it's just telling us that, so everything is satisfiable so far. And s.model, I believe, the other one. And this one would basically then return us some values for our variables that satisfy the constraints. So let's add our first constraint. So for this, we can then say, an example real quick that I wrote down for this. Just write that in. Okay, so for our first constraint, let's say that x is equal to 20. So for now, we're just going to look kind of like choose something very similar as you might have seen in like math class a long, long time ago. So a very simple formula for now, x is equal to 23 minus 2 times y. So we can add that as a constraint. And now we can ask Z3, is this still satisfiable? It is. And we can ask it to model this, give us a solution for it. And it tells us if x is equal to 1 and y is equal to 11, this constraint would pass and would be true. We can verify this. 2 times y is 22, and 23 minus 22 is equal to 1. So it seems like Z3 gave us the correct answer here. Okay, let's add another constraint. So in this case, let's model 48 is equal to 3 times x plus 3 times y. Let's check again. It's still satisfiable. Now if we have it print out the model again, so now it says x is 9, y is 7. You can try verifying that yourself. It got a little bit more complex with this, but I assume all of you could still solve this easily with your math knowledge. But what if it gets a lot more complex? So this is stuff we can still do manually. But what if it's a formula that has hundreds of variables and hundreds of constraints? And that's what you often get when you deal with real programs. If you take an entire program and do kind of this type of constraint analysis on it, these formulas can be hundreds of constraints long. And this is kind of what you're trying to solve in this part too, which you can then use to see if you can reach arbitrary points. You also, as another example, add a constraint that is no longer satisfiable. So it tells us that x has to be 9 and y 7 for this to be true. So what if we add a constraint that x has to be 1 now? If we check it again, it would now tell us unset because it's no longer satisfiable. If x is equal to 1, there's no way for these formulas to be correct, so this can no longer be satisfied. So this type of constraint solving in the realm of symbolic execution can basically be used to verify if states of the program are reachable. You can use it to prove certain properties about programs to determine if an fgets call can actually overflow or not, and stuff like that. Okay, any questions on this? Yeah.
The first equation you check and model, shouldn't it be a range? Is it just spitting out a value?
So when you say model, you ask it to give you examples that fulfill this.
Okay.
So
is there a way to ask for a range? The values?
There is a way to ask it for all the constraints that are set up. I'm not sure if you can ask it for a range. You might be able to, but I haven't used these 3 directly that much. I usually use it through the other symbolic execution library, so I provide the entire functionality. You could look at Z3's documentation of it, see if it supports that type of stuff.
You want a range of potential values.
Yeah, everything that we
You
could
just
do.
add another check to see if it's within a range, and then if that's like the first check, Z3 won't even consider the other stuff.
Okay, I got you.
Okay. Any other questions? Okay. So let's talk a bit about a couple of different types of symbolic execution. So first of all, there's the one that was more explored initially, being just static symbolic execution. This is usually based on source code. This is kind of what I also meant when I said, like when we discussed fuzzing, we talked about like gray box, black box, and white box fuzzing. When we talk about white box fuzzing, you usually talk about symbolic execution, where instead of like running the fuzzer that generates arbitrary inputs, you're basically using a symbolic execution engine to like explore the entire program state. It has some benefits that it isn't relying on compatible architecture. So if you have C code that's meant to run on ARM, x86, MIPS, whatever, as long as you have the source code, you can run it. You don't. It doesn't need to be compiled for like specific architecture. But it also has a lot of downsides. It's very hard to reason about things like kernels or libraries that aren't included with the source code. Or like doing things like reading environment variables. Since everything is static, all this information that you can't easily get through the source code suddenly gets very hard to reason about. There's one main engine that I know about that does static symbolic execution, but in general, most of the industry, from at least what I can tell, has shifted more towards the dynamic and colic approach, which is more based on actually executing and simulating the binaries instead of just dealing with source code. So the general idea of this type of dynamic concolic execution is often to combine concrete state with symbolic state. So in this case, we saw that x, for this example here, for example, we said that x is an integer and y is an integer and kind of went based on that. But this gave us a good amount of constraints. And this could be even more if it's a longer function. So what if we, as the user, say, okay, for x will always be 3. X will never be something else. I know that based on something, x is always going to be 3. This would then be concrete state. And then, but we still care about y. We still want you to solve for y. So in this case, it could completely eliminate kind of the x constraint. And since it knows that x is 3, which is not equal to 0, x can never be 0. So this entire branch would not have to be evaluated. So then you would only do the symbolic analysis on y. So x would always just be 3 in this case. Well, so you would always know that x has to be 3 in this case. And then you'd only symbolically solve for y. If there was like some other instruction there that would, for example, say x is equal to x times 2, it would then just update it in memory, and now x would be equal to 6 instead of 3. So instead of like doing all this symbolic stuff, some of the data will be concrete and some of the data will be symbolic, which in essence means that you do not need to explore every single path. Like whenever there's a branch in the program, if it doesn't work, like if the branch operates solely on your concolic data and not on your symbolic data, you can kind of just ignore the branch and just work through it concolically, and you don't have to like generate all this extra state and solve for all of that. This often has major performance and real-world impacts. Like if you're trying to run a symbolic execution engine, you just take some arbitrary binary. That binary probably has hundreds of function calls, hundreds of libraries, a lot of code that it invokes. And if you can tell it, only the code that was like taken in from like some read function somewhere, only like this buffer here in memory is what I care about. Only this X buffer. Everything else just uses as concrete value. So you'll load the binary, you start normally executing it, and as soon as the read function here, whatever it's called, that's the data you mark as symbolic. And then let's say like if an if branch, for example, operates on X, then this would be handled symbolic and like generate these different states. But if like there are branches and whatever that do not operate on your data, they would just be ignored and just executed as normally based on the concolic data. Yeah, pretty much what I said is on the slide. I don't think I pretty much all of it. Any questions on kind of this combination? So the way the symbolic execution engine that we're going to be exploring in the class does, it uses the pin tool that we discussed a few lectures ago, where you give it a binary, it loads the binary, and then the user of the library, of the symbolic execution library, can tell it what data it wants to mark as symbolic, what it actually cares about. And then it uses pin to start basically simulating the binary. And then whenever there's like data that is interesting, was marked as symbolic, that's when the engine comes in and kind of like does the symbolic stuff. which works a lot better than just going through the entire source code of an application. At every single branch, you just say, okay, I need to split up my state, because this is generating a lot of state. And you kind of want to reduce that. So that's kind of where this is extremely useful. Yeah, any questions so far? Okay, so let's talk a bit about a couple of different engine types. So start with the source code one. This is what I mentioned earlier. There's one main engine that I'm aware of that's based on source code. I'm sure there are many more that people have developed, but Klee is the most popular one. This one is based on LLVM, so you give it source code, you let Clang or whatever generate the LLVM IR from it, and then it works on the LLVM IR. This has many advantages that come with source code, such as like an easier time distinguishing between variable and pointer relations, and a lot of things like that that are, when you only have a binary, there are a lot of issues that come up. Like even just generating the control flow graph, if you only have binary code, suddenly gets hard. Like if there's like an indirect function call, like some function takes an argument and then it jumps somewhere based on that argument, like purely statically without executing the code, it suddenly becomes very hard to determine where that jump goes. So just generating correct control flow graphs already becomes really hard with purely static or only source code. So there are a lot of limitations, but also has a lot of advantages that kind of come in. In general, Klee seems to also be harder to use and integrate with other tools, but it has found a lot of popularity among some researchers. I haven't used it personally, but people do use it. Then there's full system. There's only one main one that I'm aware of, S2E. This one, the main advantage of these is that their goal is to model an entire system. So they do this by kind of injecting themselves directly into your hypervisor so they can fully control your operating system. And then you can track all like transitions, everything across like kernel boundaries, and basically track anything you want. This makes them extremely powerful because you can control everything. That's also kind of the main downside. You do control everything. So you need to write a lot of code. There's a lot of manual effort involved in actually setting them up and using them effectively. So there are like cases where these are very useful, like if you have an entire embedded device that you want to reason about, where you have a lot of kernel boundaries, or even when you want to do symbolic execution on the kernel itself. Like there are many times where it does come in useful, but it's harder to use. So for our class, we're going to focus on this kind of middle ground here, the binary analysis symbolic execution frameworks. In the practical sense, these are by far the most popularly used ones. They're used in CTF computations a bunch. They're used in the real world to find bugs. They're used to analyze crashes, help fuzzers. And I would say these two engines are probably by far the most used one, with Anger being the most used one in total. In this course, we're going to be using Triton for our project. We're going to talk more about that specifically later. And but these are two engines where you give it a binary or some user space code, and you can kind of have it do symbolic execution on that. Both of them have a Python API. Triton also has a C++ API, but we're going to be using the Python API for this course. And you basically pass it a binary. You can mark what input is symbolic and kind of goes from there. And in terms of how complex symbolic execution can be, these two engines are both fairly straightforward to use. Any questions so far? Okay. Let's talk about some challenges of symbolic execution. So in theory, what we talk about here, if this would always work, it would be amazing. This would be by far the most powerful analysis technique of all time. Like we talk about fuzzers, like they want coverage, like explore as much of the program as possible. Well, a constraint solver, you can just set up a constraint for every single loop, for every single if instruction, and you can explore the entire program that way. You never need to like worry about generating random data for coverage, because the constraint solver can always tell you what data exactly you need to go there. So in reality, there are some issues that come, however, when you're trying to use it on real programs, and that kind of greatly limits it. So in reality, fuzzers find a lot more bugs than symbolic execution, but it can be, in theory, it's super effective, but there are some very major limitations. So the first one is memory. So in the Z3 example, we saw that integers and booleans and stuff were being modeled without issues. But what if we had like more complex data structures? Like what if we have pointers or structures that have pointers to other structures that they themselves have other pointers and so on? This becomes very hard to deal with at some point. Would you want to symbolize everything? If you have something like x is equal to read from memory somewhere. And then you have an if branch if x is equal to some other value, if x equals y. Well, how do you know what x actually is? If the entire you want to put everything as memory as symbolic, so x could be anything from 0 to 255, let's say if it's a U8, then you would have 255 states suddenly. That's a lot to model. You'd have to split up your state 255 times. As you can imagine, that wouldn't really scale well. Kind of the same issue as with static analysis, you then need to abstract memory, abstract all these things in some ways, and that then kind of reduces your kind of confidence in various ways. So this is kind of also where concrete, like the kind of combination of concrete and symbolic execution comes in together and is often helpful, where you can pre-initialize memory with some concrete values that only make some values symbolic, and with that you can greatly reduce the state that you actually need to explore in this type of manner. But memory is still a very big issue, and how memory is modeled in these different symbolic execution engines is often a major difference. Like they do not always do that the same at all. Then there's the environment. So how are library calls or syscalls handled? Like we looked at malloc, for example. Like how many different branches does malloc have? Probably a couple of hundred in it. So if you look at a C program that's like int main, and the only thing this program does is call malloc, and then let's say it has like an fgets call into the pointer returned by malloc. Even if that's all it does, well, the symbolic execution engine, if it works on the binary, it would then go into the malloc library, and then it would need to generate this type of like state for every single branch, loop, whatever, every single list revolves that happens. And suddenly your actual program that you care about is very small, but your symbolic data that you generated from this is extremely large. So how do you actually handle it? Same with like kernel transitions. Like you execute a syscall, it goes into the kernel, while Anger and Triton, they do not have access to the kernel. They don't know what actually happens in the kernel. So would you model every single possible return value of the syscall? Well, you could, but in reality that doesn't really work. Mathematically you could, and in practice you can't. So there are a lot of issues that kind of come with the environment. It's like if something like any memory goes into the kernel, you suddenly lose complete track of it. You don't know what happens to it. You don't know if it's modified. The symbolic execution engine no longer knows. The kernel does whatever it wants. So there are like a couple of different approaches that are taken with this. The main one is basically to emulate the syscalls and the library calls. So you see a call to malloc. Well, you know kind of what malloc does. So instead of handling every single error condition, you just implement your own form of malloc that is called instead, and this kind of just returns a memory region without generating any symbolic data. Malloc is a very expensive and complicated call, so it's like for a lot of simpler ones, this becomes a lot easier. Like a library routine like string length, instead of having this loop for which you generate symbolic data, you just return it the length of the string very easily. It's like for a lot of these things, you kind of emulate them yourself in the engine and make them a lot more simpler, so you do not need to generate all these paths. Another thing that kind of comes in here is this concrete execution once again. If the value you pass in is concrete again instead of symbolic, it suddenly becomes very easy again. You can just let the kernel execute the syscall, and since it's only going to touch concrete value, if you only put in concrete values, suddenly it becomes a lot. This problem is kind of solved. But in general, kind of the environment surrounding it when you're running it on a real operating system pose a lot of challenges for this kind of mathematical, theoretical solution. Any questions on this? Yeah.
Can you like maintain a list of functions that you like don't want analyzed? So like say it comes across like 30 syscalls and like they're all like well-known syscalls to just like kind of like, okay, don't do any symbolic execution based on these functions.
Yeah, that's exactly what a lot of the engines actually do. Or what you might need to implement yourself for some other engines. Yeah.
They do that. How do they then know like all the returns after give like the range of valid things? Like, does it know what a value could be?
Can you give an example of what you mean?
Like if you do the 30 random library calls or whatever that are well known, and then you have a variable that might have been altered in that, how do you know like what it could be anymore?
So you don't just fully ignore these calls, you kind of emulate what their behavior would be. So let's say you have a a library call to the string length function, and it takes one argument being like some string. Inside of the real string length function, string length would not be like a very difficult one to handle, like even normally, but just like as a simple example here. So what you might do in your engine is whenever string length is called, you just hook it instead. And instead of calling string length, you define your own string length. You could even do it in Python. And then you might say, okay, the string is located at RDI, so read out the string by just reading what's an RDI at that point. And then we can literally just call the Python length function onto RDI, onto the string. And then we just do the opposite inside of the engine. We do rax.write, something of that sort, and overwrite rax with the length we calculated. So we basically hook the string length function. We don't just ignore that it ever happened, but we kind of handle it ourselves without generating any of the symbolic data and just return the result kind of. And this also scales like more complex things. Later we'll see like exactly something that looks exactly like this kind of in like some examples for Triton code where it does exactly this. Does that make sense? Okay. Any other questions on this? Okay. Well, unfortunately, it doesn't stop there yet. There are two other extremely big issues. The first one here, probably being arguably the biggest one, being state/path explosion. So earlier we had this example here where we have this function, it had like two nested if statements, and suddenly we split up the state. And we kind of generated the different like formulas. So we had like F1 and F2, and these formulas had like the Boolean formulas, and we kind of split up the states. So what happens if you have function calls, more if statements, a lot of more like state that could be either this or this? Well, every single time you need to split this up and generate a new instance. So this would be F1A then, F1B, and so on. And this grows exponentially. As you have more branches, these grow and grow, and suddenly you're left with hundreds of states. And then suddenly your analyzer can no longer handle those, like all of these states. This is kind of what's being referred to as state/path explosion. Or if you have a loop, let's say you have like some loop with some condition, and then at every single iteration, you have two constraints. One, the loop exits, and one, the loop returns and loops again. So that also just generates all these states. And in every state, you don't just need to keep track of the formula, but you also need to keep track of like all the, like if memory is modified, especially with like symbolic execution as well, like if it's a mixture of concrete values and symbolic values, you need to keep track of all the memory that's being modified. So each one of these states has like a massive memory overhead, and for each one of these states you need to manually handle, and they can exponentially grow even more. And that's a massive issue with symbolic execution. If you just pointed at the main function of even a hello world program and tell it to run, it would suddenly have like hundreds of states and start getting completely stuck. So some solutions for this. So with loops, for example, what engines often do is to, for example, put a cap on how often a loop will be executed. So it does some static analysis on the code. It realizes, okay, this is a loop. And instead of just executing it as often as the loop counter happens, maybe we say, okay, we're just going to execute it 3 times and just track the symbolic state for these, or we only execute it 1 time. With this, you obviously lose a lot of accuracy. It's far from perfect, but you can't have this massive state. This doesn't scale. There's no computer in the world that could handle this exponential growth for a larger program. So that's one approach. There are some more heuristic approaches that instead of just limiting it to once or twice executing, they kind of try to figure out maybe what's like, they do the first execution, they maybe try to figure out how often is the loop potentially going to execute. They're going to do the last execution, like something that might be like more interesting, and focus on like a few interesting states. So there are like some heuristic approaches, but in general it kind of comes down to, we can't do all of this, so abstract it away in some sense. And yeah, so that same kind of applies to like the execution traces. So kind of, you can't just exhaustively investigate every single possible approach. This is kind of where also graphing algorithms then come in, be it like a depth first search or a BFS or like various other searches that are done. That kind of, when you have these blocks, you choose some graphing algorithm in which to explore it. So you might tell the symbolic execution engine, well, I really care about a path that reaches this. And then based on the CFG, you might try to model a path to it, and then just do a depth first search straight to that region without like exploring all the other paths and like try to generate input for that. Or another approach is kind of doing backward symbolic execution. So if you have a state and you have an input that you like, yeah, okay, that's kind of what I said. Like you have like some input here and you want to like kind of go backwards and you solve each constraint from this point on. So first you solve this one and then you solve this one and so on. You kind of go backwards to like figure out an input that hits this. This can, for example, be very relevant for what you're doing in Project 5, where you're fuzzing something and you have some crashes. And then you want to figure out, well, how did these crashes actually happen? So you could script out a solution based on symbolic execution, where you go from the final input and kind of go back through constraints to solve for what the initial, for what kind of conditions caused this kind of crash. You can kind of print out like at what conditions kind of actually affected this. This is once again a situation where kind of this the mixture of concrete and symbolic comes in very helpful, because if you can mark that only a certain part of memory is symbolic and interesting in a symbolic manner, you can skip a lot of the state splitting. Because like if here you have a branch that operates purely on your concrete data that you don't care about, you don't need to actually do the split, and you can just go down the actual path. So this is one way that this type of state path explosion is also lowered, but it's still a massive issue. And that's probably the biggest issue that's kind of stopping symbolic execution from being super applicable, and what makes it very hard to use. Because you can't just point at a target like you did with AFL, for example, and tell it to run and give me like potential vulnerabilities and so on, because it's very soon going to run into these issues. So you need to manually work with the program and kind of figure out like, okay, I care about this function and these inputs, model like these, just symbolically focus on this specific part and tell me what it's actually capable of doing, and so on. Any questions on this? I would also say inside of industry itself, symbolic execution is not a technique that is used a lot. There are people that use it and use it for their work pretty well, but I would say the majority of vulnerability researchers probably just don't bother because it's often not worth the effort to set up. But I believe if someone gets really good at it, it has a lot of potential to find bugs, and some of the coworkers that I worked at internships in the past were extremely good with it and were able to do crazy things with it. Just a lot harder than just setting up a fuzzer often. It has potential, but it's something that requires a lot of work and practice to be good at. This project's going to showcase a little bit of that to you, where you're going to do some simple things with it. I would encourage you to explore it further if there's something that interests you, because it's a very extremely potent technique. It's just very hard to use effectively.
Symbolic solvers are actually like starting to get really good in terms of like, if you give it enough knowledge and you analyze things enough, you can like write ones that'll create collisions for hashes and like break hashing algorithms. There's been some that are trying to reverse like block ciphers like AES without the knowledge, or like without partial key knowledge. So they're getting pretty good. And then people are making hardware just to do stuff like that. So not just for finding bug paths.
Yeah. It's extremely effective if you're really good at using it. It's kind of the thing that you kind of need to kind of specialize on symbolic execution to a degree, become very good at it to like make proper use of it. But if you do that, it has a lot of potential. Let's talk about our final issue, being the actual constraint solving itself. So I mentioned earlier in the Z3 slides that kind of SAT and SMT solving is an NP-complete or undecidable problem in itself. So as you generate these formulas, you don't just have like hundreds of paths, but every single one of your paths is eventually going to have a formula that has like hundreds of variables, hundreds of constraints, and just solving that, since it is an NP-complete problem, does not have an efficient solution, also eventually starts slowing down a lot and kind of bottlenecking your entire process, because every single formula then starts taking seconds to solve, or even minutes to solve after a while, because it just can't go any further with this. Especially once it gets like more of the SMT formulas, not the SAT stuff, some of these type constructs inside of these formulas become very hard to model for this, especially once you like include not just integers and booleans, but it's like arrays and all these other like more complex structures. Yeah, so there are a lot of problems that come with symbolic execution. That's kind of what makes it very hard to use at times. Any questions on kind of the charms of it? Yeah.
Is it possible to do something like in the reading where they used like dynamic, or they would like analyze it without context and with context at certain spaces? So like, could you set up a range to only do symbolic execution past a certain point and just give it all the variables at like a dynamic execution?
Yes, so kind of combine symbolic with concrete, where like some states you care about, others you don't.
Yeah, but just like ignore everything until a certain point or start.
Yeah. That's actually what you're going to be doing in Project 6 as well for the symbolic assignment if you choose to do that one. So yes, but kind of. It depends on the engine. So Triton and Anger support it. I think most other engines don't. Anger did not support until about 2020 when they released an extension called Symbian, which then added support for it. But yes, it is kind of possible where you start off where you kind of just only focus on specific things. The way we do it with Triton is that we just execute a binary normally in GDB until a specific point. So that's kind of what the project's going to have you do as well, and the demo later will be as well. Let's say you have a program, it has like a main function, and this main function calls f. Say this is like the program, and you care about f. So the way that we do it for our Triton use case is we just execute the program normally in GDB and set a breakpoint on f. And once f is hit, we dump the entire memory state and register state, basically everything we write down out to disk. And then in our symbolic execution script, we load all of memory, all of registers in as concrete data. So we have like a known starting state at this point. And then we only care about like the argument to f, let's say this being RDI. And then we map RDI as symbolic. And then we have it only explore the f function using the symbolic data. So those are different ways to do it within the engine itself, where you just have it execute main normally using pin, and then once you get to f, you start doing it symbolically. This, in practice, is, in my opinion, a little bit easier, but basically same effect, and yes, that is possible. For some engines, not all of them, but Triton and Anger both support. Any other questions? Okay. Let's briefly talk about symbolic execution plus fuzzing, which you mentioned earlier. So a lot of research has gone into that, and it's not been super effective in a broad sense. So it kind of comes in the same way, like, if you're good with it, it can be good, but you need to like know when to use it, and you can't just generically use it. So if you look at all the most popular fuzzers out there right now, like AFL++, libAFL, whatever, or Onkless, none of these do symbolic execution by default. They've all had extensions written for them that do symbolic executions, but these are far less used. Because by default, you can't just attach a symbolic engine and have it do great, or like better than the fuzzer itself. So one example that kind of worked out was a combination of Anger and AFL called Driller that the Anger team built in, I believe, 2016. Actually, let's give some background. In 2015 or 2016, there was a massive competition that was hosted by DARPA, and that competition basically had teams write automated tools. It was called the Cyber Grand Challenge, the competition, and teams basically wrote tools that, given a set of binaries, automatically find bugs and automatically write ROP chains, fully automated. There's no human interaction. You are basically given a bunch of binaries, and you basically find solution and write exploits for them, completely automated. So in that competition, a bunch of people competed, and symbolic execution was a very relevant part of many of the team solutions. Just for reference, the incentive to win was about what was 750,000 for first place, and also a very large amount for some of the second and third teams. Anger got. Did Anger get first place in that?
I think so.
Yeah. Okay. I think they got first place. They definitely got like top 3. They performed really well, the team that wrote Anger. And they did a lot of tests on that. They spent a lot of effort into that. Like Anger at release had like 65,000 lines of code. Now it's a lot more. But the basic idea of it was to kind of generate exploits automatically. A lot of teams competed here, and Anger was one of the best participants. So they did a lot of really cool stuff with it. One of one of the approaches they took for that, like for the automatic exploit generation, I can talk about exactly how that worked. But they basically used a combination of symbolic execution. So after they found a bug, they used symbolic execution to kind of go through it to kind of learn about the capabilities they had, and then kind of build on top of that to automatically generate drop chain. It was really cool research that you can read if you want to. I can link a paper on Answer if you're interested. But they kind of did a lot of research actually finding the bugs. And I could probably pull up some graphics for that. Let's find that real quick. So this is the paper they released for it at the time in 2016, where they just talk about general like what they kind of built into Anger, which included a lot of like automatic exploit generation, patching vulnerabilities, and everything automated. It's really interesting and extremely cool project at the time, and still is. Just trying to find some of their result graphs. Let's talk about their placement. Where is it? No, that's not that. Okay. So this kind of like different things they tested was purely fuzzing being the blue graphs and purely symbolic being the red graphs. And they found like symbolic execution on itself, they kind of came to the same conclusions that it can't find a lot of the bugs that fuzzing kind of can, mostly because it then suffers from all these constraints like path explosion, where in the end it finds the same kind of like shallow bugs that fuzzers do. But in the end, like all this path explosion, they can't find like they can't get to the deeper bugs because like the path explodes too far. It's kind of like why when you're comparing it on like a 1-to-1 ratio, fuzzing massively outperforms symbolic execution in all cases except one. And then they attempted a technique that kind of combines both. I thought there was like some stats and graphs on this, but I don't really. Is it this one? Okay. So they tried a couple of different things. The first one being just fuzzing with AFL. They also had symbolic assisted fuzzing and so on. And in the end, using these symbolic assisted fuzzing, they did find more bugs than just with fuzzing. I'll talk about specifics of how exactly that worked in a second. They found more bugs, but later in the text, they also note that in the same amount of time, the fuzzing found more bugs. It did find more paths to take overall, but that was only after letting it run for a longer time, kind of. And I believe somewhere they say that like 3 times. Yeah. So like in reality, fuzzing identified almost 3 times as many vulnerabilities as symbolic execution did. And it's kind of like they kind of go on to explain how with the symbolic and fuzzing, or like with symbolic in general, it just couldn't, once it got to the hard paths, like the ones that were not shallow anymore, it could no longer solve for them. So their approach was, with Anger and AFL, they called the fuzzer driller. And that one kind of worked by using this Kagok execution where you would let the fuzzer run. So the fuzzer would just do test cases, track coverage, and so on. Was based on AFL. And if the fuzzer was stuck in its fuzzing loop and wasn't finding any new coverage for a while, that's when the symbolic execution would get invoked. And it would kind of go along like the paths that the fuzzer had found and try to solve the constraint at one of the paths to generate a new case that generates new coverage for the fuzzer. This was only done if the fuzzer is not finding any more coverage anymore for a long time because this is slow. This type, like every new test case that's being generated takes a lot of time. So there's a lot more literature in like the combination of symbolic and fuzzing. I haven't read myself too much into that, mostly because in industry I haven't really seen it much yet. But it is a possibility. It's just hard to do and suffers from like many of the same problems. Okay, I think we need to move on because we don't have much more time. Yeah, we don't have much time at all. So just quickly about the reasons to use Triton. It's written in C++. Concolic mode is based on pin, so it kind of integrates really well with like some of the stuff we've learned so far. Like we talked about pin and all that other stuff. The biggest advantage, in my opinion, over like Anger is that it integrates very well with other tools and frameworks. it can it can generate LLVM-IR. LLVM-IR can be transformed to something that that Triton can handle. You can basically anything that you can deal with like C++ code, you can kind of integrate with Triton really well. It's completely free, open source, and under very active development. It's being used very heavily for like malware reverse engineering, where you're using it to like the malware obfuscation technique that we talked about, where you kind of emulate everything, where you like treat malware as bytecode and like write a VM to like emulate that. There have been a lot of kind of approaches where Triton was used to like automatically retrieve the original code back from this. It has some performance advantages over Anger, but in general, the performance constraints are usually based more on like theoretical limits rather than like language limits, so it's not massive in general. But the documentation is pretty good, and it's extremely customizable, so you can replace C3 with a different constraint solver if you want to, for example. There's a lot of things you can like modify there. This is the general engine design. So it uses pin as its main way of executing the code in like in colic manner. It has a change engine. So change was like one of the techniques we talked about in a previous lecture. They can use to track data flow at runtime. It has a symbolic engine. It has like this SMT solver, and you can also use alternative programs to pin as long as they can. There's like a format called SMT2lib, and this is kind of a project that aims at having a standard for like interface for like the different engines. So as long as your backend kind of generates code in this format then it can be supported. So you can also like hook up a different type of emulator to, for example. So like a very easy to use with other tools. Then it also has Python bindings, so you can just script out your Python script instead of C++. The very rough summary, I think this was taken directly from their website or paper or whatever, but yeah. So something you can do with Triton, obviously symbolic execution. You can script your debugger with it. You can do fuzzing, code coverage. You have access to pin through higher level languages, like when you pin by itself only has a C++ API. With this, they built a Python API on top of it, which is also cool in itself already. You can convert binary code to LLVM-IR and back, so all these LLVM pass things we talked about, you can also do in this case. Taint analysis and so on. You can read more about it on their official blog. I'm just moving really fast right now because we're almost out of time. I want to showcase the tool practical as well. Internals, every instruction is kind of modeled by an abstract syntax tree and remains in SSA notation. And yeah, all parts of memory have either concrete or symbolic values, so it can be a combination of both. And yeah, analysis is done at program runtime using pin. And let's move on. Okay, let's look at the demo examples, because that's something that I think is very relevant we get to here. Okay. So let's start with demo one. So this is the C program that we're going to be looking at. This is the exact same one that we kind of explored. Actually, no, it's not. A completely different one. This is a very simple demo. In this case, we're going to not look at the small capabilities of Triton, but at its taint capabilities. So we have the main function where we call function f, and then it kind of does some stuff, returns z. In this case, we're going to track taint. We're going to track if z is tainted by x. So what we're going to do is we're going to mark x as tainted, and then during this function, at the end of the function, we're going to check the return value of the function and see if it was tainted by x, which in this case it should be, because a is bigger than 5, so z would be equal to x, so z should be tainted in this case. So let's look at how this actually looks. So we start off with our main function here. We initialize Triton, we tell it it's x86-64. Triton supports x86 and ARM. Doesn't support a lot of other architectures like MIPS and so on. For that, you'd have to use Anger, but it does support the two most popular ones. We do some optimizations, you can just ignore these 3 lines here. Then we load a memory dump. So how we're going to do this, as described earlier, we're going to be generating a memory dump at the f function and go from there. The way this memory dump is being generated is using the snapshot.py script. You kind of set a breakpoint on it using GDB, and then you invoke this script in GDB. I'm going to showcase how that looks in a second. And this is just going to dump the entire memory and register state. If you're interested, you can look through it exactly, but yeah, that's like kind of what it does. So we're going to load everything into the Triton context. So what this is going to do is going to the dump that's being generated is like in JSON, so we like, parse that out in Python, and we go through the register file and we map all these registers as concrete values. So what was dumped from the dump, we just load into the emulation engine. We do the same for memory, for like every single memory region. We just set concrete memory values and initialize all of memory and registers using the concrete values we generated, we dumped from GDB. Then we taint the EDI register, which is the argument to the F function, and then we just call the emulate function. And inside of emulate, so this is kind of the general workflow of how Triton looks. So you handle the emulation yourself. So you get the opcodes, then you have it parse out the instruction, and then you tell it to the CTX processing instruction. That's kind of what executes the instruction that's located at this opcode. So you give it a PC, which in this case, we're just going to give it what's currently set to our IP. So it's our execute the F function, because that's where we generate the dump. And then it's going to just loop through, and if we're at the return address, so this was compiled without pi, so the return address is static. In this case, this. So we're going to check. Where was it? If the PC is currently at the return address, then we're going to print out that the return was read, and we're going to check if the RAX register, which is the return value of the function, has been tainted, and if so, we print out, we have a print here. We also print out every single instruction, and for every instruction, we check if the instruction operates on tainted data. And yeah, that's the basic idea of the script. So here are some instructions of how you invoke it, the snapshotting routine. So we started this in GDB. We set a breakpoint on the F function. We run it. Then we can get the snapshot.py script into GDB and just generate the dump using full dump. And this just wrote the entire dump to /dump. Type quit, and then just execute the taint demo script. And we can see it started executing instructions at the F function. If we did an object dump, we would see that these would be the instructions there. And at every single instruction, it basically tells us if it operated on tainted data. So if you remember, when we talked about taint analysis, kind of, you have this memory region, and if something is tainted, it kind of like you set bits in like a byte in a bitmap, and so on. So the first two instructions don't. If you remember, we only mark EDI as tainted. So here it then writes EDI to this memory location, which means this instruction does operate on tainted data, and this would then mark that this memory region is also tainted. And then we once again, here we reference it again, so once again, tainted instruction. And then since this is a jump based on this compare, this is also a tainted instruction. And here we can see how the taint is basically being propagated to the RBP-4 memory region. And eventually it's going to tell us that the return value was in fact tainted. So here it moves into EAX, which is the return value. It moves data from a tainted region, so EAX is now also tainted. So this is probably at least so far from what I've seen, Triton has the best taint analysis API that I've seen. Makes it fairly easy to do this type of taint analysis. It still looks complicated, but in general, it's not that bad. You can just mark the inputs as tainted, and then at every instruction you can see, well, did this propagate the taint? Is this memory region tainted? You can kind of just ask all these questions, which can be very useful at many times. Questions on this demo? I'll release the code from that as well, so you can look at it a bit more in depth for like project reference. Okay. Then let's look at the actual symbolic demo now. So if we look at demo.c, we can see it's this is the function we had earlier on the board. Just instead of the prints and x's and stuff, we just return 0 here. And our goal is to find input that hits the return 0. So let's look at the Triton script again. So inside of the main function here, we once again say the context is 64-bit. When we load the dump, which is the exact same function as before, we just have the memory dump, and we read in all the registers and do the same for like the memory. So everything is kind of loaded in as concrete values again. Then we call the function to symbolize the inputs. So if you remember, the function that we looked at had two arguments, two integers, x and y. So what we're going to do is we say that RDI and RSI, both these integers, are now marked as symbolic values. So when we execute them, we're not going to treat them as concrete values and just execute them. We're going to actually generate the symbolic formulas for these. And then we call the emulate function, once again passing an RIP so it knows where to start. So the emulate function in this case is a bit more complex than it was before. It's a bit smaller actually. So once again, we have this main while loop where we get the instruction and then we have it executed. And then we have like some hard-coded solutions here. So once again, I took out some addresses. So our goal address, the return 0, is located at this address. To get there, we need to hit this address first. And these are two addresses that if we hit them means we fail the constraint and we're at the wrong location, so these are fail addresses. So we're basically saying if we hit one of the failed addresses, we fail to find a solution to it, and we're just going to return an exit saying that we couldn't find a solution. If we hit goal address 2, we're going to do the exact opposite. We says we hit the goal, and we basically print out the model that hit the goal. So we have it generate some values for us to hit it. Now we're going to go through the code, and we're going to check if the address is equal to this, which is the address of one of the compare instructions. So inside of the code, we have like x and y as arguments to the function. And then we have like some if statements that checks if x is larger, if x is not equal to 0, right? So here we have the first one of the compare instructions. So we're checking if this is the compare, we get the 0 flag registered. So from the compare instruction, the 0 flag will be set if it's equal or not equal to 0. And then we basically push a constraint to it, where we say our constraint is that the 0 flag needs to be 0. That's what we need the 0 flag to be at this compare to reach that. And then we're going to retrieve a model that satisfies these constraints. And then based on that model, we can initialize our concrete memory based on this model. So we look for the variables that use this, and we map all of these in. The same for the other instruction. In this case, it was a larger than 2, the comparison. So for this, we get 2 of the flags, the 0 flag and the throw flag. And for the branch to go the way we want to, the 0 flag and the CF both need to be set to 0. So we add those constraints, once again get the model, and set the concrete variables based on that. And finally, we just move on to PC. So this way, we're going to go through the code, and whenever we hit one of the 2 branches we care about, we're going to set up the constraints so that we get to the point where we want to be. And based on that, we can we have it generate like values for us that satisfy this, and then write them as concrete values to memory and say this has to be true now. So this is the general idea of this. So once again, we're going to have the same workflow as before. We're going to go into the demo, break on F, right? I'm going to run it, generate the dump. So once again, we have this dump, which else is, well, this kind of like memory map, the register, like if we, this is kind of like the format of how like everything in this dump kind of looks. It's like just a bunch of dictionaries that kind of map all of memory and all of registers. And now we can just execute this. It's going to load the dump into memory, and it's going to start emulating it, and based on the constraints, it's going to go through. And now it told us that if RDI is 0xFFFF and RSI is 0x3, this would be 2 example values that would solve the constraint to hit our goal. This was a lot for a very short time. I would have liked to have more time, but the lecture kind of went by fast. For project 6, I think the symbolic challenge is probably the hardest one. So if you just want to get by with least effort, probably do challenge 1 and 2. I think those are probably more straightforward to do. It is a very interesting technique. I'm going to push some. I'm going to upload both these examples and also link some other examples and write-ups that might make a bit more sense. I kind of wanted to kind of expose you a bit more to like the potential power of symbolic execution and what it can do. And in your project, you can play around with that a bit more. There you're going to be automatically solving a checksum function and finding an input array that is valid and goes through it validly. Something that would, for a larger function like that, be very key to do by hand. And yeah, any questions? Yeah.
What is Project 6 do?
2 weeks from today. Okay, that's it for today.